The granularity or grain refers to the level of detail in a fact table. This can be determined by the intersection of all the components of the primary key, including all the foreign keys and other primary key elements if there are any. It will help you determine the fact of the size of the fact table. So basically, it means what level of detail do you want in your fact table. Let's say you have the sales data transaction by transaction within your fact table. So every sales is one transaction. That is the level of grain in your fact table. Now, that is the finest level of data that you have available. So what you can do is you can go up from there or aggregate it to maybe daily sales, weekly sales, monthly sales, quarterly, yearly. So you can always get aggregation, and this will give you a more summarized view of your data. Sometimes if you have finer grains, then you can do market basket analysis. For example, if you have sales by sales data, what are all the products that were sold in each of the sales transaction, then maybe you can see which products are bought together and do a market basket analysis. But sometimes you may want a more aggregated view of what is happening with our sales, quarterly, monthly, like that, then you can do aggregation on the data. Like I said, fact table grain can also help you determine the size of the fact table, and kind of also gives you an estimate of what is the size of the data warehouse or data mart. Basically, you will see that usually fact tables is the table which is the most frequently updated table in your entire design here. The product, the period, the store, these are usually less frequently updated, less frequently changed, or less frequently getting more rows. But the fact table usually is the one with highest number of updates, highest number of rows. So let's get an idea of a fact table. Here's an example. So we have the product, period, store, dimension tables, and then sales, which has 6 facts: product code, period code, store code, units sold, dollars sold, and dollars cost. So we have 6 fields here. If we want to know the size of the fact table, which is the sales table, let's say we think about how many rows of data are needing to be in this fact table, how much storage or size in bytes is required for each of these rows. And that's, we multiply those two numbers, we are good. So let's find it out. Let's assume some of the things here. Total number of stores is 1,000, total number of products is 10,000, total number of periods that we are going to store in this database is 24. It means 24 months, 2 years of monthly data. So first thing I said was how many rows are there in the sales table. If assuming half the products are recorded as sales for a given month, so half the product means 5,000 products. Okay. And per month, then we have how many stores? We have 1,000 stores. So every store is selling 5,000 products and we have 1,000 stores. So let's do that number. And then, so this is all per month. How many months we have? We have 24 months. So multiply this by 24. This is going to be how many rows of data there are within your sales table. So that's how many rows. Now let's say each of these fields require 1 byte, or let's say 4 bytes. 4 bytes. So 1, 2, 3, 4, 6 fields. So these many rows into 6 fields into 4 bytes per. So if you get that calculation done, this is the total number of bytes that would be needed to store this fact table. What is a hierarchy? It's a meaningful standard way to group the data within a dimension. Why is it important for dimensional modeling? For example, there may be certain address field which has the zip, let's say, of the store, city in which the store is, and the state in which store is, you do realize that there is a hierarchy there. So one state can have multiple cities, one city may have multiple zip codes. So that hierarchy is there. How do you deal with that when you are working with dimensional modeling? One way is you ignore that there is a hierarchy, put all of these three attributes within one same table or dimensional table, and just work with it that way. If you do that, we call it denormalization. So what that does is that you may have redundant data, but you do nothing about it and just leave it there. And Kimball's model, or the star schema, prefers denormalization. If you were to normalize the data, on the other hand, what you would do is that you would put state as one of the dimension tables, then you will have city as another dimension table, and zip has another dimension table. And that way you will have three different tables which will then refer back to your store information, and that's how this will work. So if you do this, this will definitely reduce some redundancy in the data, but you may have more time needed for joining these multiple tables. So this is called normalization. And if you normalize these hierarchical dimensions, you end up with something called a snowflake schema. So let's take an example real quick. So in this case, there is a product hierarchy. This is the fact table, which is connecting to the product dimension table. But there may be that, let's say there is a product, we may have an Apple iPhone 13, which comes from a product family of iPhones, which may be in smartphone product category, which may be inside some other product categories such as personal devices. So we see that the product hierarchy is implemented via normalized dimension tables here. This kind of normalization prevents duplication of product groups, categories, and families. But when you write a query, then you will have to get data from multiple tables. This configuration is not star schema. When we make use of something like this in our design, then this becomes a snowflake schema. Here are other examples of hierarchy. You can see this is a date hierarchy in which one date, all dates will have year, quarter, and month. You may also have some other ones which have variable depth, such as this is an organization chart within a company. It may, one side has more dimensions than the other. Let's now talk about slowly changing dimensions. So we do know that in a star schema or any dimensional model, usually the fact table gets updated or changes very frequently. But dimension tables data, they can change, but typically do not change very frequently. If they change slowly. So what do we do with them? Let's say you do have a field. Let's say you have in the Blue Ridge University, you have the professor dimension, and the professors will have a rank. So we know the professor's rank may be like an instructor, assistant professor, associate professor, professor. So how do you deal with that if somebody gets a promotion and has a new rank? Well, so you have to think about, do you want to track the historical changes, or do you want to lose that data? So type 1 and type 2. Type 1 is where if the business doesn't care about tracking the changes, then what do? Nothing. You just replace the old data with the new whenever it changes, and you don't need to store what it was before. So lose historical data if that's acceptable. Databases do that quite a lot. The second type is that you care about, or you want to track about the historical changes. So you want to see from when to when the rank was a certain rank, and then when did they get a promotion, when did their rank change. For those cases, if you want to create a field which stores the current value and several old value fields that will be helpful. So for each changing attribute, you may have a current value field, which will be like this is the current value, and you will have a multi-valued field which can accept multiple values, and every old field or old data goes into that field. Here's what it would look like. So the dimension table contains several records for the same customer. The specific customer record to use depends on the key and the date of the fact. So let's say every customer will have a start date as well as a customer key, and these same fields will also be repeated in the fact table as a date key and a customer key. That's how you can retrieve data across these two tables. So there is a time element attached to the field as well. Dimensional modeling is an iterative process. You start with preparing of your tables or data, then you do data profiling and research, and finally this is the step when you start building your dimensional models. But again, it's an iterative process. So you would first make your detailed dimensional model, but that's not enough. You will go ahead, test it, and based on the testing, you will refine the model, you will review it again and again, and make sure the final model you come up with is a validated model.